This video is a follow-up to our lesson on sketching sinusoidal relations. What I want to look at is an example of a trigonometric function, sinusoidal, that is this time involving radian measure. So the first couple of examples that I did for you were both in degrees. So I'll just go through it. It's basically exactly the same thing. The only difference is our period will be 2 pi, and our angle phase shift in here will be in radians instead of degrees. All right, so if I look at this example, first thing I notice is it's not in the form y equals. So we're going to change that. So to rearrange this, first thing I'm going to do is get rid of this 3 down here. So I'm going to multiply everything by 3. So this is all considered 1 because it's multiplication together. Multiply by 3 here. Again, this is all considered 1. We never ever touch this argument. When we're multiplying, adding, subtracting, the argument never gets changed. So you just change that coefficient in front. And then I'm going to multiply this one by 3. And that's going to get rid of that. And I'm going to have, let's give myself some room here. So it's going to be negative 2 bracket y plus 1 equals 6 sine. Now, one other thing we got to do, we talked about it in our other examples with degrees, the coefficient in front of x must be a 1 when you identify your horizontal shift. So sometimes students look at this and they will say the horizontal shift is pi over 3 to the left. That would not be correct because the coefficient of x is not a 1. So what I'm going to do is fix that as I'm going across here. I'm just going to put a bigger bracket. I must factor out the 4. X plus, so now you have to divide this by 4. So just recall that dividing by 4 is the same thing as multiplying by 1 over 4, which means this is going to become now pi over 12. And you've got a minus 12 at the end. Okay, so now I want to get rid of the negative 2 next. So I'm going to divide everything. So this whole left side by negative 2. Now each term over here by negative 2. So that's all 1. And then divide here by negative 2. I'm going to be down to y plus 1 equals negative 3 sine 4x plus over 12. Negative 12 divided by negative 2, this will be now plus 6. All right, almost there. Just got to get rid of this plus 1. So we're going to now subtract 1 from both sides. So when you subtract 1 from this side, you're going to be down to what you're looking for, just y equals. So subtracting 1 from the right side is only going to affect this. It's not like multiplication. You don't subtract 1 from every term. You subtract 1 from each side of the equal sign. That's going to give us negative 3 sine 4x plus pi over 12 plus 5. All right, so make sure that our brains now are thinking radians, not degrees anymore. Now that's only going to affect a couple of things in our chart, but it will affect a couple of them. The domain, well, we know that for these ones, theta can always be anything we would like it to be. Now the range, we're going to think the range through. So I've got a 3. Again, the negative does not make any difference for your range. Just think 3 first of all. So that means, your graph is initially going to be at a high point of 3 and a low point of negative 3. That's what that 3 does out in front. Then the other number that will then adjust your range is the one at the end. So you're going to look here and say, well, now I'm going to move the graph that's running between 3 and minus 3. We're going to take that whole graph and shift it straight up in the air 5 units. Well, if we think about that, if you take 3 and move it up 5 units, it's going to now be at 8. And then if you take your minus 3 and move it up 5 units, it's going to end up at positive 2. If you look at the original wave, it was 6 units wide. Negative 3 to 3, that's 6 units. If you look at it now, It's 2 up to 8. That makes perfect sense because the wave doesn't get any wider when you just take it and physically translate it up. So it should be the same width. So I'm confident that I've got this right. Can't see the 2 very well. It's going to run between now 2 and positive 8. So the range, I'm going to use bracket notation. Smaller number first, bigger number second. Square brackets means it can include those numbers. All right, amplitude. Amplitude is always the number in front of your trig function, and it's the absolute value of it. It's always positive. All right, period. So the period is normally in degrees, 360 degrees. And the formula to get the period is 360 divided by k. Well, in radian measure, all we got to do is make that connection that 360 degrees is equal to 2 pi radians. So the formula is going to switch to 2 pi over k. And in this question, k is that number. It's always that number. It doesn't matter about this question or any question. That's always k. So the period is going to be 2 pi divided by 4. 2 over 4 reduces to half. So this graph is going to take pi over 2 radians on the horizontal scale to make one full pattern, which in degrees would be 90 degrees. Our phase shift, right here, pi over 12 to the left. Pi over 12, always indicate direction with it. Vertical translation, it's always right here. So it's going to go up 5. The sinusoidal axis is always attached to that movement because it's normally at 0. And if you take the graph and move it directly up 5 units, that's going to switch this now to y equals 5. All right, so those are all the characteristics of my graph. So the next thing I'm going to do is I'm going to write a mapping to go along with this function. So I'm just going to move things around a little bit here. If you look at this function and you're going to write out a mapping to go with it, well, our mapping will be, so this graph has x and y, and x and y. We're going to map those ordered pairs to new ordered pairs using the following mapping. So let's adjust the x values first. So remember, this will make the graph be 1/4 the width it is on the horizontal scale. So it's a horizontal compression, we'll say. It's going to be 1/4 of the original x values. And at the same time, we're going to move them all left pi over 12. Now the y values. We're going to multiply all the y values. We're going to reflect them, stretch them by a factor of 3, and then move them up 5. So I want all of that to happen. So I'm going to multiply the y values by a negative 3y, and then we're going to move those values up 5. So remember, stretches are factors. That's why you multiply them. Reflections are also factors. You multiply them. And then translations are additions and subtractions. That's why they're added and subtracted at the end. All right, so we're now ready to start getting the data ready to plot the graph. So remember, let's look here. We got sine as our base function this time. I'm just going to draw a quick little sketch here so we don't forget what sine looks like. Sine starts at 0, goes up, down, and back to the middle. Remember, it's done. Now, normally it's 360, but we're going to work in radians, so that's now 2 pi. The middle here is no longer 180, it's now pi. This angle will be pi over 2. This angle will be 3 pi over 2. Those are your quadrantal angles. Those are the only ones we use when we're sketching this. All right, so we're going to make a table of values, x and y. And we will use our quadrantals. So we'll start with 0, pi over 2, pi, 3 pi, 3 pi over 2, and 2 pi. Get these mixed up here. right, so 0, the sign value is 0. Pi over 2, the sign value is 1. Pi, the sign value is 0. 0. 3 pi over 2, the sign value is -1. And 2 pi, the sign value is 0. Feed those points into this mapping, every ordered pair. It'll output the new ordered pairs after it applies all of our transformations. Here we go. This is what we're looking for. X and Y. Okay, let's put 0 in for X first. So a quarter times 0 is 0. Take away pi over 12. The first angle is going to be negative pi over 12. Let's do all the X's first. The next one, I'm going to put pi over 2 in here. Let's just kind of do this one over here so we can see what's going on. So we're going to take a quarter of pi over 2, and we're going to then subtract pi over 12. This is going to be pi over 8 minus pi over 12. 8 and 12 have a common denominator of 24. So we're going to put this one over 24. Well, we're going to multiply by 3, so that's going to be 3 pi. This one I'm going to multiply by 2, so that's going to be 2 pi, giving me an angle of pi over 24. That's my new angle that's going to go here. Oops, it didn't work. So this angle will be pi over 24. Okay, let's do one more out. See if we can get a scale on the go here. So the next one is pi. So a quarter of pi, so that's pi over 4. And then I got to take away pi over 12. Let's just do that. Where can we fit that in? Here, maybe. Pi over 4. I'm putting pi in for x. And then take away pi over 12. Common denominator would be 12, so this will become 3 pi over 12 minus pi over 12, which will give me 2 pi over 12, which reduces to pi over 6. Now, if you want to speed this up a little bit, there's a couple ways you can do it. One is you can use the fraction button on your calculator. Now, again, I know we encourage you to be able to do fraction work in your head, and you may not have a calculator if you're doing these at a higher level than high school. However, it does speed things up for us in a question like this. They say, what about the pi? Just don't put the pi's in. So you'd put like 1/4 minus 1/12. It'll give you 1/6, and then you just got to realize you're going to have a pi in the numerator. So this one we said is pi over 6. Well, what I find is students will get here and say, well, I don't see any scale. It's easy with degrees because you'll see like 30, 60, 90. Say, oh, obviously it's going up by 30. It's not as obvious when they're presented in fractions like this. So what I suggest you do is look at these as if they were common denominators. So if I look at 12, 24, and 6, this would be -2 pi over 12. This one is -2 pi over 24. This one's already over 24, so it's positive pi over 24. Let's have a look. To go from -2 pi over 24 and end up at positive 1 pi over 24, I must have added 3 pi over 24s, which is the same thing as pi over 8, but let's leave everything as common denominators. So then, if I look at this one, pi over 6, and say, what's that if I put it over 24? That would be 4 pi over 24. Well, let's see if our pattern's holding. I was at 1 pi over 24. I ended up at 4 pi over 24. I must have added 3 pi over 24. So I can see that I'm going to add every time now 3 pi over 24. Well, if I'm at 4 pi over 24, which is what this is equal to, and I add 3 pi over 24, I'm going to be at 7 pi over 24 for my next one. So that would be my 3 pi over 2. 24. It's a mess. I apologize. Then I go to the next one. So, well, I got to add 3 more pi over 24s to this one. And you'll want to work with common denominators. This doesn't reduce anyway, but if it reduced, I would just in my head at least keep track of what it was over 24. Add 3 more pi over 24s to this one. That's going to put me at 10 pi over 24, but that reduces 10 pi over 24. I can divide them both by 2. It would actually then be on my scale 5 pi over 12. Now, it's usually at this point, if I was sitting in a classroom, where I kind of throw out a question that puts this kind of what goes on here in perspective for students. I'd always like to ask students if anyone feels that they're mechanically inclined, and some students will often say yes. Sometimes some will sit there not offering that they are. Having said that, I think this is something that all people should be aware of. If you were out in the yard working with someone and they tried a wrench onto a nut, and let's suppose they tried a 5/8 wrench. They checked on the wrench and said 5/8. And then you said, it's slightly too small. It almost fits, it's just too small. I probably need the next size up. So in the classroom, I'll say, someone tell me what the next size up is after 5/8. And often it'll be like it is right now, crickets. Even the mechanically inclined often aren't quite sure what the next size up is. Now, sometimes an experienced mechanic, electrician, or someone, they'll just rhyme those off because it's part of their job. But the average person sometimes says, oh, I'm not sure what's next. They usually bring out a handful of wrenches and try and find one that fits. Well, if I had 5/8, here's the way that wrenches work. Typically, they're built on scales of 16ths, meaning they get 1/16 bigger, the width of the opening each time. So the reason this is 5/8 is because it's a wrench that's 10/16. 10/16 reduces to 5/8. Well, if I'm at 10/16 and the next one's going to be 1/16 more, the next size up after a 5/8 then would be 11/16. 11/16 doesn't reduce. So that means the next size up after 11/16, or sorry, after 5/8 would be an 11/16 wrench. You say, oh yeah, what's in that? No, that didn't fit. It's got to be a little bit bigger. Okay, give me the next one. The next size up after 11/16, you'd add 1/16, which would be 12/16. They wouldn't have a wrench with 12/16 written on it. They always reduce it. So 12 over 16, divide them both by 4, you're at a 3/4. So always just think of the denominator in 16ths, and then either add or subtract a 16th to figure out what the next size would be. So for example, if I'm at 5/8 and say, no, that's a bit too big. What's the next one below it? Well, you have 10/16. One size smaller than that would be 9/16. 9/16 doesn't reduce. Say, okay, well, no, that's still not quite small enough. I need one smaller. Well, one smaller than 9/16 would be 8/16. But you wouldn't see 8/16 on a wrench because that reduces to 1/2. So there's how the system works on wrenches, not metric wrenches. There's another system of wrenches called metric, where they just have a number on them, which is a measurement in millimeters of the opening. Us Canadians find those ones easier to follow. 10, 11, 12, 13, 14. They don't have to do anything with fractions. Anyway, that's the little aside that I would normally go on in the classroom and you say, well, what the heck's that got to do with anything? Well, it's exactly what I did up here. I got all of these to be a common denominator, and then I figured out what I was adding each time, and that let me set up my scale. So it's kind of an analogy for that. There's my story for the day. Okay, let's do the y values. Try to get a little neater here and get kind of messy on you folks. The y values, so 0 in here for y plus 5, that will give me 5. 1 Negative 3 times 1 is negative 3 plus 5. That will be a 2. 0. We already did 0. We know we get 5. Negative 1 times negative 3 is 3 plus 5. That one is 8. Last one is a 0. We already did 0 a couple of times. That one is a 5. Well, let's look things over here, see how we made out. I got 2 and 8. Lowest number 2, highest number 8. That's what I said the range was over here in the chart, so that's a good sign. These numbers here, doesn't really matter that they're these ugly fractions. Don't worry about it. We're just going to go to our graph like we did before. And here's what we're going to do. So we're going to get a line on the go. All right, there's my x-axis. So remember what we do. We put the start and we put the end, which I look up here at my chart. And I'll come back with those. Then we cut this in half. Just eyeball it. There's about half. Cut each of these in half. And then cut this one in half. So you should have 1, 2, 3, 4 equal blocks. These will represent your 5 quadrantals that you've now transformed to these new spots. So this point will be negative pi over 12. The next one, I think we're adding 3, so it's pi over 3. Pi over 24. Pi over 24 for the next one. Next one was pi over 6. Next one is 7 pi over 24. And the final one was 5 pi over 12. As a double check, you could say, what if I put these all over 24? Is there a pattern here? Let's check. This would be negative 2 pi over 24. To go to that, it'd be adding 3 pi over 24. If I add 3 pi over 24 to pi over 24, I'm going to be at 4 pi over 24. 4 over 24 reduces to 1/6. That's good. So this one, so in our head, think 4 pi over 24. Add 3 more pi over 24s. Perfect. 7 pi over 24. That's 7 pi over 24. Add 3 pi over 24s. That's going to put me at 10 pi over 24. 10 over 24 reduces to 5 over 12. Perfect. The scale is going up by 3 pi over 12 each block. Okay, so this time now, our y-axis, we got to figure out where we're going to put that. So remember that our scale is 3 pi over 24s. So what sometimes students will do wrong here is they just randomly go and put the y-axis arbitrarily anywhere they want. Well, it's clearly between these two because you're at a negative and a positive, but you can't just put it anywhere you want. So technically there's 3 blocks in here. So 1, right? So they would be your 1, 2, 3 pi over 24s. Well, this must be your 0 here then, because this one, sorry, this must be your 0 here because you're 1 pi over 24 here. So your y scale, see how we make it with this vertical line. Not very good. Try and fix that. So we should make a line coming down through there. I'll erase that other mess that I made. I guess that'll work. Okay, so there's where my y scale would go. Now the numbers on the y scale, if you remember, they went from 2 to 8. You can compress the y scale like we did the x if you wanted to, but you really don't have to here. We will go. You can go by 2s if you want it. So I could just go, let me see here. So 2, 4, 6, 8. And you get to pick the scale. So you can go by 1s if you want. You can go by 2s, whatever scale you find works best for you. So I'm going to go by 2s. 2, 4, 6, 8. Got to scale at least one of them so I can see what the actual scale is. If you just leave no numbers here, I have no idea knowing what each tick mark represents. Okay, so let's apply our points. The first point, negative pi over 12, is at a y value of 5. So I'm going to go up here. Oh, there was my line. It is at, so that's 2, 4, so 5's halfway, approximately right there. Then the next one is at 8, I believe. Double check here. No, sorry, it's at 2. So pi over 24 is at the low point, 2. This one's back up at 5, in between. This one hits the high point at 8. And then this one comes back to the middle again, here. Here's our wave. Remember, don't turn this here because it would continue past this way. So this one's going to come down through here, up, down through here. And this will continue past that. Make sure you continue the graph at the end and put arrows because there's nothing to stop these graphs from continuing forever in both directions. So the arrows should go on there. And there would be our graph. Now let's have a look at this graph. I'm going to go to Desmos and just put it in there and we'll see how we made out. I'm trying to check your scale. So remember, it's negative pi over 12 was where we started. 5 pi over 12 was the end on the right. And my scale is 3 pi over 24, which if you do it, it would be pi over 8. And I have the equation all set and ready to go. Let's have a look here at Desmos. Okay, so I'm going to get rid of this one. First thing I'm going to do is set up my window so I can see what it looks like. The x-axis, so we can switch to radians now. We said it would, and you can actually use the pi button. Negative, you just type in pi, the letter P and the letter I, and it turns it into the symbol pi. So negative pi over 12, less than or equal to, type in the letter pi. I don't know, what did I say it is? 5 pi over 12. So 5 pi over 12. Our step, or the scale, we said was 3 pi over 24. So you can type that in. I'm going to put the reduced version in, which is pi divided by 8. Why is that not working? Axis. Y-axis. Oh, I see what it's doing. I wonder if I change this. I'm not sure it's going to actually put this numbers on that we want. No, it did not. And that wasn't 12 there, that was 24. No. All right, well, I'll show you how we can get around it. So this is all correct. It's all good. Our y-axis, I don't want a gap there, so I want it to at least go down to 0. Otherwise, there'll be a gap, and I won't see all the numbers because it starts above the y-axis. And our top number was 8, so let's give it a little bit more room. Let's go by 9. And I don't know, we can step it by 2s if you want, the same way we did on our scale. Okay, here we go. Now I'm going to type in the equation. So I have it written down in front of me here. It's y equals negative 3 sine, start a bracket, 4, another bracket. You could actually expand it in if you want to just use the one bracket, but I find that it's easier to just type it exactly like I had it. So x plus, remember pi is pi over 12. Close this bracket, close this bracket, and then you had a vertical shift of up 5. All right, there's our picture. Now my scale is down a little lower here, so I can't see it. You can just kind of zoom out a little bit. There you go. See the dots? So we'd put This was one of our dots. And no, sorry, there's the scale. Did I do wrong? Check the window again here. Okay, I was having a bit of trouble there with my scale. I wanted it to kind of model what we had done so we could check our work. So this should help us a little bit better here now. So what I did is I put my left bound, put my right bound, and I just made this step match up with these numbers, my denominator, just so that I'd be able to see them on the bottom. By putting in there the pi over 8, it kind of messed up the scale. I had to kind of search for the numbers. This way it'll make it a lot easier, and we can check. So negative pi over 12 is our left edge. Look at where it is. It's at 5. Perfect. Halfway in here, there's a dot there. Look, it's pi over, it gives you the coordinates. That's pi over 24, comma 2. Good. Our next one was pi over 6. It's up at 5. You can, that doesn't give you the pi version, but anyway, that's where it is. It's good. The next one is right here. It's up at, so there you go, 7 pi over 24, 8. That was one of our points. And then the end one, 5 pi over 12, was right in the middle at 5. Maybe in the future we might want to add a little bit more to either end, but anyway, there's no question that the scaling is a little bit more complicated when you're dealing with radians, but we are expected to be able to manage and function in both radians and degrees. So that sketch, oh, I was telling you yesterday, one thing you can do here, oops, not what I want to do, is, there's a way to copy this. All right, my apologies. After some searching around and looking at things, apparently I am not able to copy and paste this graph. I thought I could. Must be another graphing program I'm thinking of. Anyway, I was thinking I could just copy it, take it back to Smart Notebook, paste it in, and have a look at it compared to our graph that we drew, and we would see that it's very similar. But we're going to have to just rely upon what we recall from our sketch and what this ended up doing. I also changed the scale here to go by 24ths instead, and that way it lined up better with what we had sketched. There was our negative pi over 12. There was pi over 24. There was pi over 6. So you can see everything better. Okay, so let's go back to our main slide. We're on this one. So there was our sketch, which if you recall the one we just did in Desmos as a verification, it did in fact work. All right, so that is an example of what we would do to work our way through a sinusoidal relation that is presented in radian measure. Some practice questions will follow shortly.